Hello and welcome. Today, I will share with you guys a story of resilience, how we kept our systems alive when millions of users were hitting our backend. It's either our system holds or it collapses. So let's hear about that story. My name is Maaz Malik, and I am a DevOps engineer at adjoe. Together with my team, we try to build and manage highly scalable and reliable infrastructure for our applications. adjoe is an ad tech company, and through our technologies, we've built really cool mobile gaming feature that the publishers can integrate into their apps. Among these publishers, there was one publisher who had an idea to run an ad campaign during one of the biggest events in the US. Now let's try to guess which event is this. Any ideas who this person is? Yes, exactly. This is Kendrick Lamar. And where is he performing? Any guesses? Perfect. This is the Super Bowl. Super Bowl is one of the biggest events, sport events in the US. The idea this publisher had in mind was to run an ad campaign during the last quarter of the Super Bowl, and they expected to collect approximately 10 million users, and they planned to drop all of these users onto our backend in batches of 100,000 users per second. And this was for the duration of 100 seconds. So 100,000 users per second for 100 seconds is 10 million users. The normal traffic from this publisher was approximately 1,500 RPS daily, but the traffic increase was expected to be around 2 million requests per second, which is around 1,000 times the traffic increase. This was the scale for us for this event. You might now be thinking that, OK, why auto-scaling would not work here? Auto-scaling is actually reactive in nature, and it's also not very instant. Also, throughout the several years that we are in service, we never had any problem with auto-scaling. We had various promotions, various campaigns from different publishers, and we were fine. We would never intervene with auto-scaling, and it was working fine. But the speciality of this particular case was that the traffic was so steep and so high that auto-scaling would not be able to catch up because it's reactive in nature and not very instant. Reasons being that there are some delays involved here. For example, spike detection delay. In CloudWatch, if you know about AWS, there's a CloudWatch, and there's approximately 1 minute of delay in spike detection. And you might also have evaluation periods configured that m out of n data points has to be over the threshold so that the scaling can trigger. You might also have startup and initialization phase in your application where you have your liveness checks, your health checks, and you have some delay in startup of your application. So all of these delays put together makes auto-scaling not so very instant. If you're relying only on auto-scaling and you have such kind of massive traffic increase, then you would have crash systems, loss of revenue, bad reputation in the market, which would entail losing customers. So there's lots and lots of fires to extinguish here. What we need to do here is actually proactive scaling rather than reactive scaling. Now, the question is, how do you know which resources do you have to scale, or what are your potential bottlenecks? So since every infrastructure is different, you might need to think about what resources do you have. So you might have databases in your system. You might have messaging systems. You might be depending upon various third parties that might also need scaling. So you need to think about all of these resources together and validate your theory from stress test. Stress test is a part of load test, and load test is a part of performance test. Performance test is an umbrella of tests. Like it encompasses various kinds of tests. For example, you might test in your development cycle how fast your system reacts, how scalable your system is, or how stable your system is when high load is put onto it. This is called load test. And there is also an extreme case of this load test, which is called stress test, where you keep your infrastructure config static, and you put extremely high load on the system and see how many users it can accommodate or how many transactions it can make before the performance suffers. So you need to do stress testing, and then through your observability, you would know what are your potential bottlenecks. Then you make your scaling decisions based on your observability, whatever it tells you, and then you do the stress testing again in order to reach your goal. You need to go over this loop again and again so that you model the right number of users. We'll talk about two kinds of testing here. One is infrastructure stress testing, and the other is application performance test. But now let's focus on the first point. We use K6, which is an open source project by Grafana Labs for stress testing. Why did we use this tool? This is because we already have other tools from this particular Grafana Labs, which is Prometheus and Grafana, which was already there in our stack, so it was natural for us to use this one. Now let's talk about how a developer would test. So imagine that there on the left-hand side, there's a developer who wants to test, and they created some test scripts, which will create some virtual users in K6. Note that we're using Kubernetes here, and this is because we want to pool all of our resources together because the number of users was so high, and we wanted to generate high amount of load, so it's only possible when you pool many resources together, and it's not going to happen when you only use your one instance laptop, for example. Anyways, these virtual users will generate some loads on the application, and Prometheus will scrap metrics from K6, and those metrics can be viewed from Grafana dashboard to the developer. Developer can see, for example, P99 response time from Grafana, number of virtual users, or error rate, and et cetera, et cetera. There are multiple of metrics that you can see. Before diving deeper into the stress test and the results of the stress test and which resources we had to scale, let's first talk about what our infrastructure looks like so that it's easier for you to follow. Imagine that there's a user who wants to use our services. Based on the platform, they will be interfacing with something written in TypeScript or Swift or Kotlin, based on the platform. And if they're requesting for static content, they will be landing on CloudFront, where we have textual data, images, videos, etc. And if the request is for dynamic content, then they will be landing on ALB, and ALB will decide to which service it has to forward the traffic to. Note that we have not one, but 60+ services that are running in parallel, and we designed them in an event-driven way so that each of the service can asynchronously communicate with each other using SNS and SQS. Since ECS is a stateless service, so we need something for persistence. And we're using DynamoDB for that. And we're also using Redis clusters, Elasticache clusters for caching purposes. On the right side, you see that there is Druid and Apache and Kafka. Both are open source projects from Apache. Druid being columnar database, and Kafka being a streaming platform. All those events that are generated in ECS are also stored in Druid, ingested in Druid, which is powering our dashboards, which is being used by our business people to gain some insights. We're also storing these events for longer term, for further analysis in our data lake. We took some time to set up K6 properly, since it was a new tool for us, and integrated it properly into an environment, wrote some test scripts, fine-tuned them, and now we're ready to do some testing. Note that our goal is 100,000 users per second. But in our initial set of tests, we were not even able to reach 10,000 users per second. This is because of the same reason that I told you before, that auto-scaling is reactive in nature, and you need to do proactive scaling, et cetera. So this is also what was needed here. Now let's talk about which were the components that we had to scale in order to reach our goals. I'll talk about each resources in a chronological way of this diagram, but this is not necessarily be the same thing as what happened in reality, because the order can be different first. Secondly, when you do the stress test, you will see a lot of resources in your observability that needs scaling. So all of these bottlenecks have to be fixed so that you can do the stress testing again and expect to reach higher number of users, just as a side note. ALB scaling was actually a recommendation from AWS side. And how we scale it is by measuring the LCUs. How we measure the LCU, and what is LCU actually? LCU is load balancer capacity unit. It is a measure of AWS measures load balancers in LCUs actually, and it consists of 4 dimensions: new connections per second, active connections per minute, process data per hour, rule evaluations per second. Imagine that your app is getting very low traffic, which fits under one LCU. Let's now just focus on the first dimension. It's a lot to take in. 10 new connections per second, which fits way under 25 new connections per second. But imagine that the traffic is increased now suddenly to 300 new connections per second. Now, since only you crossed only one dimension, even then you need 12 times more LCU, which is 25 times 12, 300. So crossing only one dimension makes it more, you need more LCUs for that. Based on our calculations, which was also provided from, the calculations were done from stress testing, the measurements were taken from there, and based on our calculation, we got to know that we need not only 1, but 3 load balancers. In normal one load balancer scenario, all the traffic is going towards one ALB, so it's like fairly easy, classic thing. But in 3 load balancer scenario, you have to specify which portion of the traffic is going to each ALB. And how do you configure that? You go to router 3 record. You configure the weights of each portion of the traffic that will be forwarding to each load balancer. And this is also called sharding, which is essentially load balancing the load balancer. And you have targets, which is essentially ECS services, which are registered in each ALBs so that each ALB can forward traffic to each ECS service. Now you might think that we've done enough for ALB at least. We have 3 load balancers now. We have multiple LCUs, like way more than before. But there's one more thing, very important point. You need to reserve those LCUs so that your load balancers can handle this traffic. Why? Load balancers are also auto-scaling behind the scenes. So if you put immense amount of traffic increase onto the cold node, it will not be able to scale in time. So that's why your extra traffic will be erroring out. So that's why you need to reserve LCUs, which is actually pre-warming the load balancer so that your traffic can easily pass through the load balancer. Let's talk about ECS scaling. ECS scaling itself is not very hard, like simple, not very difficult. But actually, the point here was that since ECS is backed by EC2 instances, we had to do something there, something as a preventive measure. We're running spot instances for most of our production workloads. And this helps us to to save a huge amount of cloud span. So that's why we had to, in order to prevent outages, we had to switch from spot to on-demand instances. And in order to have guaranteed capacity, we did it 3 days before the event until 12 hours after the event. While doing stress testing, we got to a point that we were not able to send more than 9,000 messages per second. And this was because we were hitting a quota limit from AWS. For what we had to do first was request more capacity from AWS. Secondly, we batched our messages together and also compressed them, due to which we were able to efficiently use what we are provided, efficiently use the capacity that we are provided. Let's now finally talk about DynamoDB. DynamoDB works in 2 modes. One is on-demand mode, and the other is provision mode. On-demand mode is where you have limitless capacity. Provision mode is where you have certain limits on your provision, on your capacity. But so for this event, we put some tables on-demand and some were still on provision mode. But regardless of this mode, there was one problem that we faced, which is called a hot partition problem. So what happened is when we were stress testing, we were not able to reach more number of users beyond a certain point. When we saw our metrics, we saw that there was one table that was throttling, that was having read throttles. Upon investigation, we found out that this is the hot partition problem. And now I will try to explain what is the hot partition problem. But before that, let's see how DynamoDB briefly works. DynamoDB stores your data and spreads it into different partitions. And a partition key decides to which partition the data would go. Each partition here actually can independently scale to 1,000 write capacity unit and 3,000 read capacity unit. A hot partition problem happens when multiple users at the same time access same partition key, overloading the capacity of the partition. So this was the problem that we faced. Why can't we detect this from our metrics? This is because AWS does not expose partition-related metrics. So what you need to do is enable CloudWatch contributor insights in DynamoDB in order to see what are your hot partition keys, meaning what are your which keys are those which are accessed multiple times and causing the hot partition problems. In our case, the problem was that there was this config which was particular for this publisher that we are talking about. And since we are simulating for this publisher, so all of those users were getting this same config. So that's how we ended up into this hot partition problem. What did we do is moved this config from DynamoDB to Elasticache, which is Redis, which did not only saved us read on the DynamoDB, also the network calls, but it also made the application more performant because it was now in cache. Note that we had TTL enabled in our Elasticache, so even if the config gets changed, it will be evicted after some time, and the users will get eventually the new config. Our friend is back. Pre-warming here is also required, just like ALB. They are also scaling behind the scenes, as I mentioned before. So you can configure it easily by going to DynamoDB settings, configure warm throughput there, and they will pre-warm your DynamoDB tables so that all your traffic can be easily handled. I mentioned about quotas when I was talking about SNS. So when you have this massive traffic increase, default quotas are usually not enough. So what you have to do is request these quotas weeks before, because AWS actually handles each case differently and takes some time to respond and analyze the case, and then they will increase your quota. So you can easily track your limits by going to service quota dashboard in order to know if you are actually hitting any quota limits or about to hit any quota limit, so that you can request it way before then you hit the quota limit. We'll now talk about application performance test. When we were stress testing, we and you also might see some issues related to your application, like application getting crashed or using more resources than it's required to do or it's intended to do. So in order to get knowledge about what is your system doing, what is actually happening in your code, you can do something called profiling, and every language these days allows some kind of profiling. By profiling, what you can do is detect these time-consuming functions, or you can detect memory leaks, or just if you want to know what is the flow or dependency of one code onto the other, you can also do that with that. We used Pyroscope for profiling. Pyroscope is actually also a product offered by Grafana, also open source. And it creates something called flame graph. This was the flame graph that we created for the application that was having some problems. The problem the application was having was it was using way more CPU than it was intended to. So when we created this flame graph for it, we found out that there was multiple TLS handshakes happening. And the context here is that the application was communicating with DynamoDB. And since TLS is actually a CPU-intensive task, having it multiple times, it's way more CPU-intensive. So how we fix the problem and identify the problem? We went to the related GitHub issue and saw that and found out that TLS session can break due to high periods of inactivity, and only max connections per host will be able to reuse the TLS session. So we simply had to change these keep alive parameters in order to fix this issue. Note that our goal was 100,000 users per second, but finally, after many times of stress testing, we were able to reach it. And this is an example of iOS target. So out of those 100,000 users per second, 60,000 was the target of iOS, and the rest was for Android. And we were successfully able to reach all the targets. This is a screenshot of only the iOS target achieved, which was taken at that time. So you can see 60,000 users per second, and the P99 response time was also not very much. It was 30 to 50 milliseconds. Now I want to show you what actually happened on that day. It's the Super Bowl day. Everyone was in the office, and it's 4 a.m. in the morning because it's Hamburg time. It's not US time. So this was a small picture of that event, and this was what happened.
Did you see this postbacks?
Yeah. The system stayed stable, and we were able to handle 100,000 requests per second over 15 minutes of period. And the best thing was that the system remained stable, and we actually were confident on that. There are some lessons learned. You need to ideally start preparing months before. We started preparing 3 months. It was good time, but still we were barely able to manage. So since this is because we had so many testing, so many learnings along the way, so many challenges to face. So I would recommend to add some more buffer to it. Also, you need to have confidence on your system that if your system will be able to handle this massive traffic, you need to have some numbers from stress test. That's very important. And I cannot reiterate more enough that observability is very important here. If you have proper observability, you can only then you can identify those bottlenecks, and then you can scale those bottlenecks. So if you don't have any observability properly, you won't be able to detect it. Then you need to integrate these stress tests inside your CI/CD pipeline, meaning in your development cycle, so that you won't have any unexpected issues while you're preparing for such kind of event. At the end, I want to say that it's not only about scaling the resources, but it's also about fostering a culture of hardships, of teamwork, of learning and testing together. And we had so many problems along the way, but we solved all of them due to teamwork. And this is very important for us. So thank you very much. That was it. Any questions?